So this is a video on the Fundamental Theorem of Calculus, Part 1 and Part 2, which are, as you can tell from the title, Fundamental Theorem of Calculus, they're kind of important. Sorry, I said that wrong. I should have said the Fundamental Theorem of Calculus. It's really probably the proper way to say that. So we're going to start with something you already know. And in class, we talked about this relationship right here that and I introduced this new symbol, the integral symbol. And we know that this first part, of course, is what we've been working on, Riemann sums. So you can find the, you can approximate the area between a velocity equation and the x-axis. Well, you can approximate the area between any curve and the x-axis by breaking it up into little rectangles and find the area of each rectangle and add them up. And then we discovered that if we let the number of rectangles be n, and then let n approach infinity using the limit process, then we're no longer estimating the total area under the curve, but we're actually finding the exact area under the curve. And so then what we made a connection with just recently was that you can do that same process through this, what is called integration. And you can see that the f function goes there, and this, the width of the rectangle kind of goes with the dx. Okay? And what we're hoping is that this process is a lot easier than the limit process. So today's video is making the connection or to finding out what this integral is. So in the first part of the Fundamental Theorem of Calculus, I have it written out here, so I'll just read through it with you and then try to explain it. So it says if f is a continuous function, and you all know what continuous means, that means there's no breaks in the graph. This is function on, I should say on the interval from a to b. Notice that the endpoints are included, so the first requirement is f has to be continuous on this particular interval. Then we'll let this other function named g be the antiderivative of f. Now, do you all remember what antiderivative is? That means a derivative, antiderivative would just undo a derivative. So essentially g of x is defined by this. I'm going to grab a highlighter real quick. Sorry. G of x is defined by this. There's that little integration symbol again. Okay? So in other words, another way to say it kind of in layman's terms is that g prime of x is f of x. So, or another way to say it is if you take the derivative of this integral thing, you will get back to f of x. Whoops, I wrote that wrong. That's not right. Oh yeah, no, that is right, sorry. Okay, so basically derivatives and integrals undo each other. You could say they're the inverse of each other. So we know that you could, so here's another look at it from a graphic perspective, that if we're trying to find this area right here, that's exactly what the integral does. So if we're taking the integral of f of t dt from a to x, you can see that we're going from a to x, then that is the g, that is the function that's defined by taking the integral of f of t, where f, of course, is this line up here. Okay, so that's basically the first part of the Fundamental Theorem of Calculus is telling you that is telling you that integration and derivative are inverse of each other. You undo one by doing the other. Okay? So for example, if I take the derivative of x squared, right? You all know that we will get 2x. So what this is telling me, if I integrate 2x dx, then I will get x squared. So one function, one operation undoes the other. Okay, that's the idea. So now we'll go to the fundamental theorem of calculus part 2. If f is a continuous function on a to b, so the same condition as before, and capital F, notice that's a capital F, not a lowercase f. It's important to notice. So this is different than that f. So, and capital F is the antiderivative of f. So in other words, f prime, capital F prime is equal to f. Then, if you're integrating lowercase f, the way you do it is you take the antiderivative of lowercase f and you plug in the limits of integration. So that's this right here. This is an important thing to remember. This is how you evaluate what we call a definite integral. A definite integral is an integral that has limits of integration. In other words, it gives you the interval over which we're looking. Now we know that we can approximate that, right? Because this is the same as the limit process, that we know that we could take the integral from a to b of f of x dx, and we could break it into a bunch of rectangles. We could say, oh, let's do b minus a over 4, and we'd multiply that by f of possibly 0 plus f of b minus a over 4 plus f of 2 times b minus a over 4, etc. So I could break that into Riemann sum and do it, but what this is telling you, what this little blue area is telling you, there's an easier way. If you can find the antiderivative, then you can just find this same process by just plugging the two endpoints in. So let's look at one that's really interesting, like for example, the integral from 1 to 2 of x squared dx. So in other words, if I'm trying to find, here's my x squared, there's 1, there's 2, whoops, that's not really x squared, sorry. Here's my x squared. So there's 1, there's 2, right? So I want to find that area. Now we could break that up into a bunch of little rectangles, and we could say, let's break it into 4, for example. So that would be 1/4 times, 1/4 times, let's see, that'd be 5/4 squared plus 6/4 squared plus 7/4 squared plus 8/4, or 2 squared. And I could approximate the area. But what the fundamental theorem of calculus part 2 is telling me, that I could do that same, I could do this easier and actually find the exact area by just find the antiderivative of x squared. So what is the antiderivative of x squared? Well, in other words, that's asking, where did x squared come from? Well, it must have came from x cubed for sure, because the derivative of x cubed is going to be x squared. But if I just take the derivative of x cubed, I would get 3x squared. And since I'm looking for not a 3x squared, just an x squared, then I would put a little 1/3 out front here. So now let's check it to make sure. Is the derivative of 1/3 x squared equal to x squared? I'm sorry, what did I do? I'm sorry. Is the derivative of 1/3 x cubed equal to x squared? So if you take the derivative of that, 3 times 1/3 is 1, drop the power 1, and sure enough, we just get x squared. So this 1/3 x cubed is the antiderivative of x squared. And so we're going to evaluate that both at 1 and 2 and subtract them from each other, because that's what this says right here. The blue, that's what it's telling us to do, right? And this is just the way we write this notation. So notice I went from here to here. So I've taken the antiderivative. That's why I have 1/3 x cubed here. And instead of leaving this like that, because it just shows that I took the antiderivative, I still haven't plugged in the 2 and the 1, so I wrote it with a straight line now on the other side. That's just the way the notation works. Okay, so then to evaluate this, I'm going to do 1/3 times 2 cubed plus 1/3 times 1 cubed. And of course, that would be 8/3. Why I put plus, that should be a minus. Minus 1/3, which would be 7/3. So what does this tell me? That tells me the area under the curve, or the area between the graph and the x-axis from on the interval from 1 to 2 would be 7/3. So there's an example of fundamental theorem of calculus. And now you can see why I've had you practicing your derivatives, because if you can take a derivative, then you should be able to undo the derivative. So let's go back to here and the moral of the story. The moral of the story is the derivative and integrals are inverse operations of each other. So if you have a function and you want to get back to if you have the derivative function, you want to get back to the function, you take the integral. And let's explore this a little bit more. So remember, derivatives are rates of change. So in other words, if we have a velocity function, if I integrate that, that will give me a position function. Right? Because the derivative of a position function is a velocity function. Or if I have an acceleration function and I integrate that, that'll give me a velocity. In general, if I have any kind of a rate of change, if I integrate it, I will get the total, a function that gives me the total change. So in other words, if I have a function if I'm integrating a function that is the flow rate of water. If I'm integrating the flow rate of water function, then I will get a total water function. That makes sense. So just like when I take the derivative of something, I know that that gives me the rate of change of that something. So when I'm going backwards, I'm going from the rate of change back to the total thing. So that's the connection between antiderivatives or integrals and derivatives, and it also gives you the connection between this new symbol and all these Riemann sums we've been doing. So hopefully that'll set you up to be able to do a lot of the worksheets that I have on Canvas. So that's where we need to head next, is just start practicing this idea of connection, understanding truly to kind of the philosophical understanding of what an integral is.